Okay, well, so in this video, we're going to look at acceleration. So the previous videos all focused around constant velocity where there was no acceleration or the acceleration equals zero. Now let's talk about what happens when the acceleration does not equal zero. So anytime an object changes velocity, we say that it is accelerating. Okay, so that's important. When we change the velocity, we accelerate the object. Now, most of the time, we'll just simply talk about the average acceleration. So the average acceleration is defined as the change in velocity divided by the time taken to make this change. So we're going to say A is equal to delta V over delta T. Okay, just like when we talked about velocity was change in position over time, average acceleration is change in velocity over time. Now, if an object is slowing down, its velocity vector and acceleration vectors are in opposite directions. That doesn't necessarily mean that your velocity is positive, your acceleration is always going to be negative. Just understand when the object slows down, okay, its vectors, acceleration vector is opposite direction of the velocity. So if my velocity is to the right, so if I'm doing like a motion diagram, right, and let's say I'm slowing down, basically what I'm doing is I'm going to take the same piece. So the red's my velocity, the blue's my acceleration. And so I know I didn't draw the second red arrow big enough, but let's say that's our vectors. So then this new vector, my new velocity is that size. Okay, and so after a second, it becomes that. And then again, if we have the same acceleration, my next vector would be that short until we get to zero. Okay, now if they point in the same direction, they speed up. So if I flip-flopped all this, the object is going to be speeding up. Now, we also can talk about instantaneous acceleration. So it's defined as the limiting value of the average acceleration as we let the time interval approach zero. So again, like what we did with, so the instantaneous acceleration is the limit as delta t approaches zero of delta v over delta t. So again, we're going to make that very small, okay? But again, this kind of notation, right, this limit as delta t approaches zero of deltas tells me that the instantaneous acceleration is just simply the derivative of the velocity, or dv dt. But it also, if v, right, is the derivative of position, put the squared in the wrong spot. That makes acceleration the second derivative, right, of position. Now, in calculus class, this is a very common stack of equations that or graphs that you'll see. So if and this is the example from the instantaneous velocity video. So you can see that I'm given the equation, right? X equals 2.1 t squared plus 2.80 m. If I take the derivative, I get a line. So the derivative of a parabola is a line. Okay, and then if I take the derivative once again of v, I get the acceleration, right? And so this is a horizontal line. So you could see that the acceleration here is constant, because once I get down to its graph, okay, it's a flat horizontal line. Now let's look at some example problems. A car accelerates along a straight road from rest from 90 kilometers per hour in 5 seconds. What is the magnitude of its average acceleration? Okay, so the first thing we'll need to do is convert 90 kilometers per hour, right, to meters per second. And so this is an easy conversion. So 1 kilometer is 1,000 meters. 1 hour is 3,600 seconds. Okay, I'm gonna get my calculator. And so it's going to be 90 times 1,000 divided by 3,600. And so it's going to be 25 meters per second. And so now I can do my average acceleration equation, delta V over delta T. So it's going to be 25 minus 0, because remember, rest means the velocity is equal to 0, over 5. And so it's going to be a positive 5.0 meters per second squared. Now, in fact, we don't have to put the positive, because it tells us that it's just looking for the, sorry, I keep wanting to put the positive. It's just telling us that it's looking for the magnitude, right? So when we just say magnitude, our answer is just the number, right? So again, that's an average acceleration problem. So let's look at one in which we have, we're looking for an acceleration at a particular point in time. So the position of a particle is given by the following equation: x equals 2 meters per second cubed times t cubed plus 2.5 meters per second t. What is the acceleration of the particle at t equals 2 seconds? So we're going to write our equation, and I'm going to kind of skip a little, or not put in units. Okay, so we know velocity is the first derivative of position. So again, use the power rule. So the derivative of x to the n is n times x to the n minus 1. And so I'm going to bring this 3 down, multiply it by 2. It's going to give me 6. And then I'm going to do 3 minus 1. That's t squared. Okay, same thing here. I'm going to bring, remember, anything without an exponent there is t to the first. I'm going to bring 1 down. And then I'm going to do t times, or t to the 1 minus 1, which is 0, which is just 1. Okay, so there's my velocity equation. And now I'm going to find the acceleration by doing the velocity, or the derivative of velocity, which again is the second derivative of position. So again, power rule, bring the 2 out front. So I'm going to say 12, right? Because 2 times 6 is 12, and I'm going to do 2 minus 1. And so my acceleration, and I'm going to look for the acceleration at t equals 2, is going to be 12 times 2, which will be positive 24 meters per second squared. Okay, so there is my instantaneous acceleration at 2 seconds. So this is an example. Anytime you see that word instantaneous, right, or you're looking for a acceleration at a certain point, you're going to have to take derivatives. Okay, so that's it for this video. And then in the next video, we're going to look forward to doing some of the constant acceleration kinematics.